So Moshe, yeah, let them.
So just to tell everyone that this is being recorded. So if you wish not to be recorded, just mute and what's the visual equivalent of mute? Unvisualize yourself or devisualize yourself, and you can turn off the closed captions by clicking on it and then turn it off. So it gives me immense pleasure to introduce our first speaker today, which is Tom Henzinger. I can probably spend the next half an hour telling you about Tom Henzinger, but I won't spend that amount of time. He is the president of IST. He's the founding president of IST Austria, which has emerged as a powerhouse of research in Austria in computer science, but also in other parts of science. I was on, I think, the 5-year review committee, and I was just enormously impressed by the speed in which it rose to such strength. And he's a fellow of everything. Here's a little funny story. He's a member of National Academy of Science. He was nominated as an international member, but I think when it came to actually doing the paperwork, they realized that they find out he's a US citizen still, so he did become a member. Is that true, Tom? Yes. Yeah, so now he's a member. So that means you can nominate him. Now this comes with a responsibility. So he's going to tell us today about quantitative and approximate monitoring.
Okay, thank you, Moshe, for the introduction. And let me also, for those of you who haven't heard, let me congratulate Moshe on the Knuth Prize. I mean, this
Thank
is
you.
Well deserved, and it's also a recognition for this community. So it's
yeah, that's I think even more important.
I will, you know, as slides, as title, I've chosen actually an upcoming LIX paper with my student, Ege Sarak. I'll keep it a little bit more high level and talk more generally about monitoring, a topic that I've gotten into the last couple of years after basically spending most of my career on really static verification. This is the monitoring setup I'm talking about. The important thing to remember is the monitoring I talk about, or the runtime verification I talk about, is both online and black box. It means the monitor can observe the inputs and the outputs to the system, but doesn't know the internals of the system. So that's a black box, and it's online in the sense that the monitor has to keep up with the system. Does the monitoring in real time, and mathematically it means the monitor can do only a bounded number of operations per system operation. Actually, this happens to be a model that goes back a very long time. Michael Rabin published papers in the early 1960s on what was then called real-time automata, and it was essentially this model that you had a bounded amount of computation per observation. So why do I think runtime verification is interesting at all? And maybe I invite you actually to a little bit of discussion at the end of this, because I imagine there might be this might not be so uncontroversial here in this group. Because you know, even I had sort of the view runtime verification is sort of a little bit sort of the totally lightweight version, basically testing, and what we want is real verification, quote unquote. But I think there are two trends that really are in favor of runtime verification. One is, I mean, hardware parallelism has been increasing and is steadily increasing. You know, we now have many core processors, we have computer clusters, data centers, and so on. And not all of these hardware resources will go into performance. And I think instead of them going into, we just talked about, into, you know, Bitcoin mining, they should hopefully go, some of these hardware resources should go into assurance. In a sense, you know, why doesn't one core on a multi-core processor watch the other cores, what they do? And the second trend is that software at the same time is growing ever more complex. I mean, I don't have to point out, you know, that we have ever more machine learned components. The cloud is involved. These things are hard to verify. And I would claim that the static verification gap is only increasing. By that, I mean the gap between, software complexity is growing faster than our ability to catch up with on the static verification side. So I think both of these are actually very good arguments in favor of runtime verification. And mathematically, actually, runtime verification is quite nice because, well, here, just Moshe's Knut was just mentioned. It was all about the automata theoretic view, right? In that sense, static verification is an emptiness problem. Runtime verification is a much simpler problem. It's a membership problem. It's asking if one particular behavior of a system, satisfies the specification. And that gives us much more freedom in terms of specification languages to start with, and also verification formalisms. There's no need, for example, really to limit yourself to finite state methods, because there's in many cases, at least in the theoretical sense, the decidability boundaries of specification languages have been chosen because of the emptiness problem. And for membership, we can suddenly deal with much richer formalisms. And I'll show you, we will use registers for runtime verification. And the other nice thing, I think, is that, it is a topic that also has been dear to my heart for years, is that verification in many ways is too Boolean. Specifications are either satisfied or not, right? Systems are either correct or not. And while this binary world is not the real world, right? In the real world, a system may be, many systems that satisfy the specification, some are better than others. And even of those that are wrong, those that violate the specification, some come closer than others. But it turns out, and I don't think anybody has done it very successfully, it's very hard to capture this mathematically, because ultimately you need a metric on systems or between systems and specifications. And these are difficult objects. While metrics are distances between traces, how close does a single trace come to satisfy a spec? They are much more natural to define and easier. And I think that's another big advantage of runtime verification. In other words, it's much easier to come up with approximate methods for runtime verification. And a second point I want to make here, and this is, I've said a little bit also in the particular setting that I find most attractive, is we think of the monitor as really being independent of the system. You want it ideally to be written by a third party, so there cannot be any collusion between the system and the design and the monitor design, because I think that's important for using random verification for security as a matter of trust. It should be unintrusive, not only meaning black box, but also low overhead. This is very important. Otherwise, it will never be used in practice if the monitoring itself costs a lot and slows down the system. And I already mentioned online. I'll have to, just for reference, I'll talk about things that occur in these 4 papers. Let me, in the interest of time, move on. So I'll start with this very simple property I want to monitor, response, and I'll write it down here in linear temporal logic. We want every A to be eventually followed by a B, and we have 4 kinds of observations: A's, B's. T stands for tick. It's supposed to remind you of a clock ticking. And O stands for other. And this is, for example, one infinite word is a behavior we're observing. And such a behavior, such one trace, either satisfies this response property or it doesn't. So response is of course a difficult property to monitor because it's live. Every behavior can be every finite behavior can be extended to satisfy a response, and it's also co-live. Every finite behavior can be extended to violate response, right? By adding, say, an A and no more B's. So response is sort of classically the most difficult thing to monitor. It's certainly not finitely monitoring at all. You cannot have a verdict that a response property is satisfied after any, or violated for that matter, after any finite prefix. So what's I make it here more monitorable by going from response to bounded response, where I'm writing here in a metric temporologic location, but I simply want to say is that every A is followed by a B within 5 ticks. This is no longer live, because now you can have finite violations. For example, an A followed by 6 ticks. The property is already violated no matter what happens afterwards. The other hand, it's not safe, because you can have an A followed only by other things. You will never, it's violated by the infinite word, because the A is not followed by a B, but it's not violated by any finite prefix. And it is technically it's co-life, so you can extend it it can extend every finite prefix to actually violate a property. So this bounded response is, because its co-life, is what is monitorable according to one of the classical definitions of monitorability that go back to Pnueli and Sachs. I'll call it simply PZ monitorability, and that's an existential notion. So Pnueli and Sachs said a property is monitorable if after any finite prefix there's at least one possible future, one possible infinite extension, such that the monitor can come to a verdict. And in this property, there's always the extension that violates the property, and therefore this is Pnueli-Sachs, or existentially monitorable. Let me make the first point I want to make about monitoring, is that actually monitoring something which is very interesting is assumptions. And I add here for the assumption that there are infinitely many ticks. This is what the second line here, infinitely many ticks. If I restrict my universe of infinite behaviors to those that satisfy this assumption, then suddenly these things become more monitorable. For example, bounded response is now what I call negatively monitorable under this assumption. Every negative verdict can actually be given after a finite number of steps, because under that assumption, it can never be that there's an A and then only other, never a tick. There have to be infinitely many ticks, and if there are infinitely many ticks and the property is violated, that means before the 6th tick there has to be a B, and if this doesn't happen, if there happen to be 6 ticks without the B, then it's violated, and you can discover this and monitor this, reach a verdict after a finite prefix. So assumptions can help in monitoring. And assumptions, of course, how do assumptions come up? They either are something you know about the system, or there's something you know about the environment. For example, the assumption that there are infinitely many ticks, you simply know about the environment that time advances and diverges, right? So it could also be if you decompose monitors, if you do decentralized monitors, assumptions from one monitor can of course come from another monitor. And there is actually, for every property, there's a weakest assumption that makes the property monitorable. I will not go through the proof of this. I just want to point this out in case you're interested in this. It's actually, I think it's very nice theory. It's in the end, it's pure topology. It's simply an argument under Cantor topology. And if you just look at, here's the proof, and just to show you the last line, you simply construct the weakest property that makes such a property monitorable using these topological operations. This is just one point I want to make. The second point I want to make is that don't restrict yourself to finite state in monitoring. I mean, use whatever can be executed in the monitor. For example, having registers. So then there's the immediately interesting question is, what can you actually monitor with a limited number of registers and a limited kinds of operations on registers? For example, if you have only counters. And here, look at the property I call P2 at the bottom, which says that in an infinite word W, in every finite prefix of this word pi, there is more A's than B's. So in any finite prefix of the infinite word, there should be more A's than B's. Well, obviously with 2 counters, you can monitor this. And here is a simple monitor of this safety property. You should simply read as long as this monitor can proceed. There's an enabled transition. The property is satisfied, and as soon as as soon as when the word is being read, an observation is being read, and there's no enabled transition, then the property is violated. So you can think of there's some sync state that rejects that I haven't explicitly given. Now, for this property, you know, if you think about it, it's not very hard to convince yourself you actually need two counters for this. That you cannot do it with one. It actually turns out you can generalize that property. Suppose you have not two letters, not only two letters, not only A's and B's, but K letters. And you say in every finite prefix of the word, there has to be more K's than K minus ones, more K minus ones than K minus twos, and so on. You actually need K counters to monitor that online in real time with only a bounded number of monitor operations per observation. So there's an infinite counter hierarchy, and that makes it already this quite interesting, quite different from the computability hierarchy that collapses at two counters. You can also skip the next thing, but you can, for example, I give you here an example of a property that you cannot monitor with any number of counters. It's a property actually that's quite of some practical interest. It simply says, you know, think of the input word is a sequence of segments between these numbers symbols, and no two of these segments are the same. For that, actually, you need an infinite number. You cannot do it with a finite number of registers, even if you can add or multiply registers. But that's, of course, an interesting security property, right? For example, this is exactly the definition for the nonces in security. So there are interesting expressiveness questions here. The next question I want to point out, and this is what the paper actually, whose title I chose, is all about, is so far I've only talked about really, you know, reaching a verdict in a finite number of steps. But there's quite some value of thinking as monitoring, as looking at the limits of verdicts. For example, if you monitor response, you might actually come up with the following. The monitor is issuing the following verdicts, right? As long as there is an appending A that hasn't been acknowledged by B, the monitor shows false. And when there's the matching B, the monitor shows true. Until there's an other pending A, the monitor shows false, and then the monitor shows true again. This is a very natural monitor. What's the property of the monitor? Well, it happens to be the lim sup of the verdict sequence is exactly the property value. We call this monitoring from below. I mean, monitoring from above is the dual thing where you take the lim inf. And if you look at monitoring, what we call here limit monitoring in that way, that you look at actually at the limit sequence of the verdicts, and do they give you the property value, or how close do they come to the property value? You get immediately a mathematical notion of approximate monitoring. And why is this limit monitoring interesting? Because number one, it's universal. It's no longer just existential like Knueli-Sachs, because you can actually require it for all behaviors that your monitor verdict is below and comes as close to the property value as possible. Secondly, you can immediately generalize from non-Boolean to from Boolean to non-Boolean property values. So it can be very quantitative. And thirdly, limit monitoring can be speculative, right? I already showed you here a sequence of a non-monotonic verdict sequence, you know, where you go back and forth between true and false. Of course, a monotonic verdict sequence is more interesting, but the monitor gives you, you know, over time always a more precise verdict. But of course, you can do a lot more with speculative monitoring than just with monotonic monitoring, and it's interesting to look at this. Just how to make this quantitative, I just give you the example now. Suppose we don't want to monitor just response, but we want to monitor response time. How many ticks are there between an A and the subsequent B? Suppose we want to monitor maximal response. Well, you can do this with two counters, right? Obviously, you count the number with the first A, you start counting the number of ticks until there's a B. And then with the next A, you have another counter that's, and as long as it counts 1, 2, 3, 4, it's still below the maximum no so far. But when there's the fifth, then you start updating your maximum. It's 5, 6, 7 is here the maximum response time. So with two counters, you can monitor maximum response time from below exactly. But obviously there's a trade-off between precision and number of resources you have. Just as an example, if you want to monitor average response time, with counters, you can only do it very approximately. If you have the necessary operations, you know, basically you need to be able to divide to compute averages, then you can, of course, do it exactly again. And it also shows the difference between a monotonic verdict function as a maximum response time and a non-monotonic, whereas the average response time, where actually the average response time may go up and down over time. So I'm looking at time, I'm already very late, so I'm gonna skip the definitions and everything. I just wanna point out, you can also go here from the discrete world to the continuous world, of course. You can go also to a probabilistic world where this is very interesting, where monitoring is not just about the past, but about actually predicting the future. If you know that your observations are generated by a probabilistic process, say a Markov chain, then you actually can use monitoring to predict the future. Just as one example is, suppose you want to monitor the mode of a sequence. So if a finite alphabet, the mode is the letter that occurs the most often. You know, to do real-time monitoring about the past, you need as many counters as there are letters, because you really need to track every single letter, how often it occurs. But if you want to just monitor the mode, predict what will be the mode with probability 1 in the future, if the sequence is generated by a Markov chain, actually it turns out you can do with 4 counters. And it's a very beautiful algorithm, I think, where you just take long and longer sequences of your behavior, and you just find out the mode of each segment. And since the segments become longer and longer, you with probability 1, you will actually find out what the mode is, even though you just need 4 counters to always remember the longest, the mode so far, and compare it to the most common letter in the current segment. And I think now I'm at the end. And just as takeaways, I think monitoring, once you move to this quantitative view, you can trade off, and this limit view of monitoring, you can trade off precision, resources, and the strength of assumptions. There's much interesting theory to be done. And I've just summarized here some of the things I tried to show you, but I want to leave a little bit of questions, so sorry for taking so long.
Thank you, Tom. Thank you. Very interesting. So let me take the first question. Can you can stop sharing so we can see the audience better. So, you know, in another area where, of course, we talk about limits is in probability theory, right? I mean, you toss a coin and the limit it will you know, will get something. But typically, it's not enough for us because we want to know how quickly does it converge? And we have various theorem about rate of convergence, because otherwise, you know, I mean, the limit is a very abstract notion. In reality, our life, we all die at the end. What is it? In the long term, we're all dead. And so can we talk about somehow here about rates of convergence of observations or verdicts?
Well, obviously, if you have if you don't have a probabilistic model that generates a system, basically a probabilistic model that generates your observations, then you cannot say anything about convergence. But even in the last case where your observations are generated by Markov chain, you can it's actually, I think it's at least I don't know of any way of saying here anything about convergence. Yeah, I think and the rates of convergence you get from the mathematics seem to be totally impractical.
Interesting. Okay, Madhu has a question.
Yeah. So so the general motivations you gave for monitoring also hold if you just treat the monitor as a piece of software that you write. But I think what you're doing here is more like, synthesizing monitors from declaratively from specifications, really, rather than just monitoring. So I was wondering whether there's any work on just building monitors using software and just verifying them to be correct using the specifications that you seem to, the specifications that seem to come up in monitoring seem a little different. And I wonder whether there were any approaches to statically verify human written monitors.
I'm not aware, but I'm not really firm in that community yet. So there may well be stuff. I mean, what has astonished me, how much there is really about basically what I would say finite state formalisms, where the theory is nice, but I think it's too restrictive. And about these, for example, even if you have just counter monitors, there's very little theory out there.
Thank you.
Other questions?
I'll ask one, Tom. So instead of putting time bounds, could you use the could you use a measure of how much time has elapsed between the request and the response, as a way of indicating that you're dangerously in the limit you're going to violate the property?
Yeah, but the thing is, if it's really a non-deterministic or worse, an adversarial system that you're monitoring, the future is going to be as bad as it can possibly get, right? So I don't see how you can make any statements about limits unless you have know something about how these observations are generated, say probabilistically or something.
No, but you could use it, for instance, to take a recovery action when a certain threshold is being breached.
That I think is a very, very interesting direction. I should say also much in runtime verification does focus on exactly that go beyond monitoring to, some people call it enforcement, others call it shielding and so on. Basically where the monitor can take corrective action. And there is quite a bit of work on that, again, mostly on finite state formalisms.
Okay, any other questions? So Moshe is just
I have a question. Yeah, hi Tom. Yeah, nice talk. So when you are counting resources, so I think in streaming algorithms, you would count number of bits, right? So even if you're counting, then that would grow logarithmically as the the size of the input prefix increases. And wouldn't that be a more robust measure than say number of counters? Because if you keep the number of operations abstract, then I don't know if it's if that's really a good measure. Number of bits is very clear.
This is a good point, but this is about the if you have a counter model of monitoring, the counter itself can be unbounded and still cost you just one operation, right? If you want basically unbounded counters, then of course, but there's many fields in which we make this abstraction, right? That I don't know how valid it is in practice.
Yeah, but viewed differently. I think all this literature on streaming algorithms then could be useful, right? Because they're like very precise in terms of how do they count bits, and then also these approximation things, and so there could be a connection there.
Yeah, that's actually a good point. There is actually, I think there's a few disjoint communities that really were, I mean, streaming algorithms is one. I think there's also a lot but maybe that's connected to the streaming, I don't know, but in online databases. That also seems relevant, and there's in algorithms there's a lot, but they tend to focus on, like in online algorithms, they tend to focus on specific problems. You know, what's the best algorithm to solve this problem, rather than generic specification languages to you know, to monitor any specification that can be expressed in a certain language.
Yeah, thanks.
Thank you, Tom. Yeah, applause. So let me move to the second talk. So Moshe has just left. He'll be back later on, and he'll be there for Rajiv's talk. So it's my pleasure to introduce Sanjit Seshia, who is a professor in EECS in UC Berkeley. He's the author of a really fine book on cyber-physical systems with Edward Lee. He graduated from CMU and works on really a number of a range of interesting topics, you know, having to do with AI verification, and cyber-physical systems. So his talk today will be on algorithmic improvisation for verified autonomy. Sanjit.
Okay. Thank you, Shankar. This talk is in the general area of formal methods for achieving the goal of verified AI-based autonomy. And there are many facets, of course, to formal methods in this domain. So I think formal methods can play a very important role in precise programmatic environment modeling. And these systems often operate in fairly complex environments, can be used to specify properties mathematically, and as well as quantitative, as well as Boolean properties. Of course, develop algorithms for verification and testing, and also formal methods for provably robust system design, which also includes aspects of runtime monitoring and assurance that we heard about in Tom's talk. But in my talk today, I will focus on a particular aspect of this, which is on the role of randomness in formal methods for autonomy. And if you'd like to learn a little bit more about the other aspects of what we've been doing on these topics, you can see it in the paper at the bottom of the slide, as well as this website. So let me give you two examples of where randomness can be useful. So imagine you want to train or test a data set generator for an object detecting neural network. For example, in the self-driving domain, you wanted to generate images of bumper-to-bumper traffic. Well, as you can see, there's really, even in something like bumper-to-bumper traffic, which is a particular type of traffic, there's a huge and diverse space of possibilities. And a model that incorporates randomness can help you cover it well with certain distributional properties. Or imagine that you are designing a robot, a learning-based robot that has to surveil a particular area, and it has to visit a certain number of locations sufficiently often. But there's an adversary, and what you'd like to do is make the robot's trajectory hard for the adversary to predict. So randomness can also play an important role here in generating random but safe trajectories. So in both of these applications I just mentioned, randomness is essential, but there's also formal specifications that the systems must satisfy. In the first case, you have constraints on well-formedness of generated images, like objects shouldn't intersect. In the second case, you have safety constraints that you don't want the robot to collide with another object. So the question here is, how can we design a system with random, prescribed random, but controlled behavior? Okay, so this is really the topic we call algorithmic improvisation, or also control improvisation. It's a framework we have developed over the last several years for the automatic synthesis of systems, reactive and otherwise, with random behavior, but also satisfying formal guarantees. And there's basically two kinds of formal guarantees you can think of. The first is guaranteed safety, which we encapsulate using hard and soft constraints. The second is guaranteed randomness, which is you want the system to be random in a prescribed manner. And in fact, that's with respect to other problems in that people have explored, that's an important novelty. That is, we want the specification to prescribe a particular type of random behavior of the output of the system being synthesized. Okay, so before I get into the guts of the talk, I want to acknowledge two people who have been absolutely instrumental in this work. I began this work actually as a collaboration with my late colleague, David Wessel, who's a professor of music at Berkeley. And in fact, music improvisation was our first application. But then I realized that there's a lot more applications in computer science in general of this particular idea of improvisation. And that turned into the PhD thesis of my student, Daniel Fremont, who's now a faculty himself. Okay, so here's the outline for the rest of my talk. I'll tell you what the problem is of control improvisation. Then I'll give you some theoretical results about this particular class of problems and talk about efficient algorithms as well as hardness results. Then I want to spend a little bit of time on an approach we call language-based improvisation, which we've used for design and analysis of machine learning-based autonomy. And then I'll wrap up. Okay, so let's start with the definition. So let's go back to these two applications I mentioned, robotic surveillance, where you want a robot to patrol an area in an unpredictable way. So let's say there's three kinds of specifications you want to write. First, there's a specification that you want the robot to satisfy. It has to visit a certain number of certain set of locations sufficiently often. Secondly, there's a constraint that is more quantitative in nature. So you want it to take a route that's close to the shortest one to save energy, for instance. And then the third is your randomness constraint. You don't always want the robot to take the same route, right? So these are three kinds of constraints. We'll call them hard constraint for the first one, soft constraint because there's a quantitative nature for the second one, and the randomness constraint for the third one, okay? For the other application, for data generation for neural network training, you have similar things. You have a hard constraint, objects should intersect. You have a soft constraint that you'd like the data to be similar to real world data, but you also want diversity, right? So again, you have a hard constraint, a soft constraint, and a randomness constraint. All right, so these and many other applications that we and others have explored, you can think of as a problem of generating sequences of letters from an alphabet, right? Subject to three kinds of constraints. The hard constraint is that every sequence satisfies some property. The soft constraint that we formulate in the talk today will be most sequences satisfy a property. And then the randomness constraint is that no sequence is generated too frequently. It's on the output of the system being synthesized. Okay, and control improvisation is a problem that captures these three requirements. Okay, so let me now get to a more formal definition, and the components are the follows. So imagine, again, let's imagine a little example here. So imagine you have two robots at these two triangle locations, and you have these four circles in the middle and a square obstacle. Now the robot at the bottom right it has to move, and the way it moves is in discrete steps. So it can move north, south, east, west. And imagine we're only looking at a bounded horizon plan for it. So a plan of length 30 steps. So a hard constraint can be that you want the robot to visit all circles while avoiding collisions. A soft constraint is that, well, most of the time you don't want it to visit a circle twice. Okay. So let's just think about what this looks like, right? So all possible plans for this robot are essentially strings in sigma n, where sigma is the alphabet north, south, east, west. But some of these are unsafe, right? So these are examples where the two robots collide. So what we'd like our output to be is to exclude all of those unsafe trajectories, right? So the set H is basically the red set, which we'll also call as set of improvisations I. Okay, so everything satisfying the hard constraint, the safety constraint, but it could violate the soft constraint. It might visit the same circle twice. Right. So now the soft constraint is the light blue set that you see here. We'll call those the admissible improvisations, right? And so those are going to be those that satisfy S in turn, like this one. Okay. So the formal definition is as follows. You're given a hard constraint H, a soft constraint S, a length bound N, and certain parameters epsilon, lambda, and rho. And we'll call a distribution over sigma star as an improvising distribution if, first of all, every string that's generated satisfies the hard constraint. Then every string that's generated with high probability satisfies the soft constraint. And the randomness requirement is going to be that you don't generate any string too often or too little. So you've got an upper bound as well as a lower bound on the mass that you assign to any string. Okay, so that's an improvising distribution. And the problem that's represented by this tuple of HS, etc., is said to be feasible if an improvising distribution exists for that tuple. And an improviser is simply a probabilistic algorithm that samples from D. Okay. So as a very simple example, let's go back to what we saw earlier, right? So imagine that this, for the sake of the slide, these are the only plans possible. And if you have epsilon, which is the probability with which you violate the soft constraint, is as 1/4, and rho, which is the upper bound on the probability mass, also as 1/4, then you can, if you simply wanted to sample within the inside region A, that won't do, because at least one of those strings is going to have probability bigger than 1/4, right? So one strategy is that you return one of these three, A1, A2, A3, with probability 1/4, and then you return one of these two that violate the soft constraint with probability 1/8, and then you will get a valid improvising distribution. Okay, so that was the sort of non-reactive setting where the environment is sort of a known a priori and not adversarial. We've also extended this problem to the reactive setting, where you now have a two-player game. You have the system and an adversary that's alternating picking symbols, so the turn-based game. And again, you have hard, soft, and randomness constraints, except that now you want these constraints to hold against every adversary, right? So you want the system to basically generate a strategy, a random strategy, where if you look at the trace of the actions taken by both players, that trace satisfies the hard and soft constraints. Okay. Now, so now this is a form of randomized reactive synthesis, of course, for bounded time. As an example, we can take the little example I showed you earlier and make it reactive by making the other robot actively seek to collide with the first robot. And then you can have the similar hard and soft constraints as we talked about earlier. Okay. All right. So now that I've told you what the problem is and given you some examples, let's look at what we know in terms of the theory of this. Okay. So when is it possible to solve a control improvisation problem? Now, it turns out that the feasibility of a problem simply requires certain constraints on the sizes of the set of strings satisfying the hard and soft constraints. Okay. And a theorem that we have here is that a control improvisation instance is feasible if and only if the cardinality of the set of improvisations is at least 1 over rho. Remember, rho is the upper bound on the probability with which you generate any string, and a similar constraint for the cardinality of the set of strings that satisfy the soft constraint. Okay, and so if you're able to count and estimate the cardinalities of these sets, then you can check if it's feasible. All right, and so now, what does a synthesis algorithm look like? Well, you take an instance and you turn that into an improviser. The improviser is the program that is generating these strings, right? And we'll call that synthesis algorithm an improvisation scheme. And what we'd like, of course, is an efficient improvisation scheme. So a polynomial time improvisation scheme is basically an algorithm such that given any problem instance C, it will return an improviser if C is feasible and otherwise bottom. And further, both the improvisation scheme and the output program it generates run in time polynomial in the size of the instance, right? So that's ideally what we'd like to get. Okay, and so in fact, we give a generic approach for generating an improvisation scheme. Okay, so, and it relies on the following operations. So if you can, given a class of specifications that you express your hard and soft constraints in, if you can efficiently take the intersection and difference of these specifications, if you can restrict a specification to a given length, so you project the strings down to a given length, and if you can count the number of words satisfying a spec and uniformly sample from those words, then we have an efficient improvisation scheme. Now, of course, this is non-trivial in general because it involves problems of counting and uniform random sampling from specification sets. right? And we know that, for example, if your spec is expressed as a Boolean formula, right, this is the model counting problem or the uniform random sampling problem, right? So you're looking at sharp p-hard problems. But in certain cases, you can get efficient algorithms for counting and uniform sampling as well, right? So there is a polynomial time improvisation scheme, which basically involves the following steps, right? And so the idea is very simple. You really construct the specifications for the ones that satisfy the hard constraints, soft constraints, and their difference. You check the feasibility, and then you sample with the right probabilities. Okay. And so we've looked at various classes of specifications, like DFAs, where we had examples in robotic planning and music, context-free grammars, where we have looked in the context of software fuzz testing. And we have polynomial time schemes for certain restricted classes, like DFAs and unambiguous context-free grammars. But for almost everything else, it's at least sharp p-hard. Okay. And also, I should mention here that if you express specifications as Boolean formulas, you can potentially build on the advances in approximate model counting and uniform sampling to get something that is an approximately correct improvisation scheme. Now, in the reactive case, the situation is somewhat similar, right? So again, feasibility reduces to counting, and in this case, there should be sufficiently many ways to win the two-player game. We call this the number of ways to win as the width of the game. And in fact, the feasibility constraints are, they look exactly the same, except you replace the cardinalities of these by the width, right? So what is the width more formally? It's the number of winning plays of the game minimized over all possible adversaries. Okay, and so here's the expression, and let me walk you through this. So here, sigma is the actions taken by the improviser. Tau is the actions taken by the adversary. So given a sigma and a tau, you get a trace, a W with some probability, right? So that's the probability of obtaining a particular trace. And then X is a set of possible traces. So now we're counting the number of possible traces that satisfy a constraint X. And now you're basically minimizing over all possible adversaries and maximizing over the choices of the improviser, right? So that's sort of counting a number of quote unquote winning plays. Okay, so in any case, that's the feasibility constraint in this case. And so the algorithms for reactive improvisation are given in our CAF paper. I won't go into it, but in terms of what we know about the complexity, again, if you have your specifications expressed as DFAs, or the game is essentially a simple reachability or safety game, then you have a polynomial time improviser. And for everything else, including LTL and linear dynamic logic, you have p-space. The problem is p-space hard. Okay. All right. So, so this is something that is also practical.
Sanjit?
Yes.
Yeah. Can you wrap up in maybe about 3 minutes or so?
Yeah, absolutely. Yeah. So, so this is something that's fairly practical as well. So for the DFA style specifications, we've been able to synthesize improvisers that we have actually generated code from, and as this is what you're seeing, a visualization of an experiment that we ran in collaboration with George Papas and Vijay Kumar's group at UPenn. The drone is visiting these squares on the right, and it has to periodically return to a base station on the extreme left. All right. So I just want to wrap up in the next 3 minutes on talking about another form of improvisation that is called language-based improvisation. And this is the other application I mentioned at the start, which is you're generating data for training and testing and verification of machine learning-based autonomy. And the approach we took here is slightly different. We decided to design a programming language, in fact, a probabilistic programming language, to essentially express hard, soft, and randomness constraints. So this language is called Scenic. We published this work at PLDI about 2 years ago. And Scenic looks something like this, right? It's designed to be a readable embedded DSL in Python. This is a little Scenic program modeling the scenario of a badly parked car. I won't go through all the details, but the idea is every time you, so this program defines a distribution over 3D scenes, and every time you execute the program, you get a new random sample that you can then render with a renderer like the one in the GTA 5 game, and you get an image like the ones that are visualized. Recently, we've also extended Scenic to model dynamic behavior. So now you have the same badly parked car, but now the badly parked car pulls into the path of the approaching ego vehicle, and that's specified using these behavior functions. And now the same way you can render now simulations using the state-of-the-art simulators, in this case, Carla. Okay, I'm just going to give you a little sense of what improvisation can be used for in a very practical setting. So in conjunction with another set of algorithms for verification that we published at CAV 2019, where Scenic is used to model the environment and the characteristics of the system for this, we've done 2 case studies that I want to mention very briefly. One is on verifying a system for automated taxiing that was a prototype from Boeing, where Boeing wants, has a neural network mounted on the right wing of this plane, and the neural network's task is to try to keep the nose of this plane aligned with the center line. And so what we wanted to do was first model the system in Scenic. So model different types of semantic features that can be changed, that can vary, and you want the neural network to be robust to. The property that you're verifying is that after a certain transient period, you want the centerline tracking error to be bounded by 1.5 meters. Using Scenic and the backend falsification algorithms in the Verify toolkit, we were able to very easily find lots of falsifying runs. This is an example of one. So early morning, low light, light rain, and you see the plane just drive off the runway completely. But then you want to make the system robust, right? So one of the uses of Scenic is, of course, data generation. And we were able to use data generation in a targeted fashion to generate counter examples that we use to augment the data set. And what you're going to see here is that the behavior of both the original neural network as well as our retrained neural network after, on the exact same environment configuration. The bottom one is after retraining with the counter examples generated from the Scenic program. Okay. Another interesting real world case study that we have again used improvisation in is in going from simulation-based verification to real world testing. And this is a case study we did with AAA and LG at one of the big AV testing facilities in the Bay Area. And in this case study, we have a real autonomous vehicle that has to follow the blue path. So it starts in the bottom right corner, has to end in the top right corner. But along the way, there is a pedestrian who has to cross at this point, right? So the pedestrian starts at the yellow dot, has to get to the red dot, but hesitates in the middle of the road. So once again, we wrote a Scenic program to formally model the scenario. I won't go into all the details, but here's some snippets of the model of the ego vehicle and the pedestrian car. And then we used our tools to generate tests and falsification that showed that there can be collisions between these two agents. And then we implemented it along with our collaborators on the test track. So here you see a portion of the test track, and we analyzed the gap between what we see in simulation and what we see on the road. And there were, of course, some things that were different, but broadly, what we saw that was unsafe in the simulation also ended up being unsafe on the road, including a collision scenario that you'll see in the video playing here. And for the most part, if the system was safe in simulation, it was also safe on the road. So here you see a pedestrian dummy, as they use typically in crash testing. And in this particular case, the perception system seems to have completely missed the pedestrian dummy, even though it detected it originally, right? And so this is the kind of thing that we can do with Scenic. You can use it for formal modeling of these sorts of complex scenarios, use them for simulation-based verification, but also translate this to real-world testing. Okay, so let me conclude here. I think this has been quite a journey on a topic that started with a sort of whimsical collaboration in the area of computer music, but now I think it is developed into a really interesting framework in computer science for randomized synthesis. We've been exploring many applications of this to the general area of safe autonomy. And I think for the future, I think this is a really interesting application that we need to also explore in a theoretical sense more. So one of the things we're looking at right now is to use improvisation for randomized exploration of a design space by changing the kinds of hard and soft constraints we look at. With that, let me conclude. And if you're interested more in this topic, we have a website, algoimprov.org, where we've put all our material. Thanks, and I'm happy to take more questions.
Thanks, Sanjit. Yeah. So any questions? So there's one from Suprati. Go ahead.
Hi, Sanjit. Yeah. So the aircraft taxiing example that you showed, so you said that after retraining and then using the same environment parameters, it sort of stays on track.
No, sorry, I might have misspoke there. So the specific video, the specific traces I showed you, both those traces were with exactly the same environment parameters. So you're seeing the behavior of the original neural network as well as the retrained neural network, but starting from the same environment.
Yeah, but during the retraining, was the same environment parameters used, or?
Yeah, so the retraining, so the environment is defined by the scenic program, right? So it's basically, you have those, the features that I went through rather quickly, and then they have associated distributions over them, right? And so in the retraining, what we are doing really is changing the distribution to focus a bit more on the counterexample and the concrete environments, that is the concrete instantiations of that model that produce counterexamples.
I see. So perhaps the training happened using some other environment parameters which sort of matched the semantic description given by the.
Yeah. So what happened originally is that the folks at Boeing, they implicitly, I mean, I don't think it was a deliberate decision, but they implicitly ended up training the neural network at a particular time of day in particular weather conditions. And so obviously you saw that bias, that it wasn't able to do well in low light and light rain and so on. And so now the counterexamples we generated, actually, I skipped a whole bunch of analysis we did, which is in our CAV 2020 paper. But the counterexample analysis showed us where, what kind of environments were problematic for the neural network. And then using that analysis, we adjusted the distribution in the scenic program and retrained.
Okay, thank you. Thanks.
Yeah, thank you.
Okay, Madhu?
Yeah, so I had this, very nice talk. I was wondering whether, you could use this in the setting of GANs, and in general, adversarial methods in machine learning to train networks, because it looks like you could generate, this could be the adversarial component in a GANs network, right? In a GANs training network. And also perhaps in, in adversarial machine learning, you could use these as ways to generate examples that throw the current machine learning algorithm off.
Absolutely, absolutely. In fact, what we are doing here is what I call as, what I and Somesh Jha call as semantic adversarial learning. So the sort of the distinction between what we've been doing here and what most of the adversarial ML community does is we operate over the semantic feature space. So we perturb things like the time of day, the model of the car, the color of the car, the position on the road, things that correspond to the semantics of the system. Whereas the adversarial ML community broadly, especially in the image case, they tend to work on the pixel space, concrete space.
Yeah, but I think the GANs, I don't know whether you've looked at GANs, but in GANs,
yes.
I think there is they do look at all kinds of.
No, there is the latent space, but it's not interpretable in the same way that we have in scenic. So the short answer is yes, absolutely. We can use this in a GAN style setting as well. But the point I wanted to make is it has to operate over the semantic space, right? So the generation, right, that has to operate over an encoding over the semantic space. And if we had that, then of course we can do that. we can use it with GANs. And but you can also see what we are doing as a form of adversarial ML, except it's not it's operating over a different space, right? So generation of counterexamples that we're doing is also a form of adversarial ML, but it's working over a different feature space.
Okay, so I think we've run out of time for questions. So, but continue posting any questions you have for any of the speakers on the chat. And you know,
Okay,
Pavithra, if you can share your screen, we can move to the next talk. Thank you, Sanjit. Great talk. Okay, so the next speaker is Pavithra Prabhakar. So she's a professor of computer science at Kansas State University. Her main research interest is in formal analysis of cyber-physical systems with emphasis on both theoretical and practical methods for verification and synthesis of hybrid control systems. He'll be speaking on abstractions for scalable verification of AI controlled. Oops, I lost her screen.
Yeah,
so her internet connection is unstable, so you know we have to watch out for that. AI controlled cyber-physical systems. Pavithra.
Yeah, thank you. Able to hear me?
Yes.
Okay.
And we can see the screen as well.
All right, thanks. So I'm going to talk about some abstraction techniques to scale verification of AI-controlled cyber-physical systems. So here is a brief introduction to what verification means in the context of CPS. We are looking at essentially software-controlled physical systems. So we have a physical system and a software controller which senses the state of the physical system, makes some computation based on the state, computes an input which is fed back to the physical system. And we want to ensure that this closed loop system behaves in some correct manner, and given the safety criticality of the applications in which CPS arise, formal verification is a must. So let me start by giving an example of a closed loop system. Let's consider a very simple example of an autonomous vehicle with a lane controller, whose objective is to essentially keep this vehicle on the lane. And what you see in this gray region here is the lane, and the brown region is the center of the lane. So initially the vehicle moves along some direction, and when it hits the edge of this brown region, then the controller applies some corrective action to bring the vehicle back to the lane. So here's a very simple model of the system. The variable x of t represents the distance of the vehicle from the center of the lane at some time t. And u of t represents the horizontal velocity that the controller applies at any time t. And I'm going to again look at a simplified discrete time dynamics of the system. So it consists of a very simple equation where the state is updated based on the current velocity. And given a velocity u of t, you know what the state, how the state evolves. Now, here is the state feedback controller, which senses the state x of t and computes g of x of t, which is the velocity that needs to be applied. And if the state is within this L and R, that is, the car is in that brown region, then no horizontal velocity is applied. So the vehicle just moves along a vertical direction. And if it is to the right of the brown region, then a velocity of -1 is applied, which is the corrective action to bring the vehicle back to the road. And similarly, if x of t is less than L, then a velocity of 1 is applied. So in terms of the execution of the system, you have an alternating one-step computation of the dynamics and the controller, and you alternate between those. So initially, the system starts in some state x. The controller senses it and computes a corresponding input, which is feedback to the vehicle. And the vehicle then updates its state based on this input. And then the new state is sensed by the controller. It computes the next input. The state gets updated and so on. And we are interested in specifications similar to in other scenarios. Here we're interested in checking that the vehicle always remains on the lane, which is a safety specification. And so the crux of such safety verification algorithms, of course, is in computing the read set of the system. That is, we have some set of initial states and some set of unsafe states, and we want to compute this read set. So we need two primitives to compute the read set in this particular scenario. One is we need to be able to compute the post of the dynamical system. That is, given a set of states and a set of inputs, we need to be able to compute the next set of states. And we also need to be able to compute the post with respect to the controller. That is, given a set of input states, we need to be able to compute the corresponding feedback that the controller computes. And once we have these two primitives, we can iterate over the two until we reach a fixed point and we have the read set. So what I'm going to talk about in this talk is AI-controlled CPS, wherein the controller is now replaced by an AI-based component, such as an artificial neural network. And classical controllers are more and more being replaced by these AI-based controllers because they can react to dynamic and uncertain environments, and also for other computational reasons. So autonomous driving and airborne collision avoidance are some examples. And so one of the benchmarks I'll talk about later in the talk. So again, the broad approach for verification, one could use a similar framework. We can compute these posts with respect to the dynamical system and then posts with respect to the controller. There's a lot of work in the hybrid systems area on computing posts with respect to the dynamical system. So this is not an exhaustive list, and I'll not get into too much of that in this talk. So the other part, the challenge appears from the fact that this neural network, a deep neural network in particular, is a highly nonlinear complex function that somehow we need to compute posts with respect to. And I'll focus on that part of the post-computation problem. So here's a quick primer on neural networks. You have a bunch of nodes, which are arranged in layers. There's an input layer, output layer, a bunch of hidden layers, and then there is edges between consecutive layers, which have edge weights, and there are also biases that are associated with nodes. And the semantics is essentially consists of two steps. One is a linear transformation followed by application of an activation function. For instance, the value of the node at some S prime is going to be the weighted sum of the nodes, values of the nodes in the previous layer, where the weights correspond to the edge weights, and finally adding the bias. And we focus on an activation function, which is a ReLU function, which is essentially the max of the value and 0. So if X is positive, the value remains the same. And if it's negative, it gets reset to 0. So once we know how to compute the value at a node, we go layer by layer and compute the values of all the layers until we get the value for the output. So the output range analysis problem is given a set of initial valuations to the input layer. What is the set of output valuations to the output layer? So here for simplicity, we'll consider just one node in the output layer and hence compute the output range. So one could use a constraint solving based approach to compute the output range, wherein you encode this input output relation using some constraints. Let's say encoding of XS, where S represents the value of a certain node S. And we could write a constraint based on these variables that encodes the input output relation of this whole neural network. I'll give a little bit more details on that in a bit. And once we have this input output in relation encoding, we can compute the output range by solving a maximization and a minimization problem over these constraints. So in terms of computing the input output relation, we could first focus on just computing the input output for a certain layer and then compose that. For a certain layer, if we ignore the ReLU operation, it's essentially a linear constraint. You're essentially saying that the value xs prime at some I plus first layer is just a linear combination of the values in the previous layer plus a bias. So these weights are some constants and xs are the variables. And if we have the ReLU function, then we essentially want to say that if this linear constraint is positive, then xs has that value. And if that is negative, then xs prime, the value at a node in the next layer, is essentially 0. And in order to encode these constraints, there is a standard encoding called the big M encoding, which uses an auxiliary variable called qs prime, which is a Boolean variable with value 0 or 1, and a constant m, which is some coarse upper bound on the values that any node in this network can take. And this encoding essentially encodes exactly the ReLU function and the input-output semantics of a particular layer, including the ReLU function. This is not quite a set of, it's just not a bunch of linear constraints over reals, because we have these variables which are Boolean. And so this is a mixed integer linear programming problem. So in terms of computing the output range, there's work on encoding this input-output relation as a mixed integer linear programming problem, as well as other satisfiability modular theory problems. And as we all know, these are all NP-complete problems. So the challenges in terms of scalability arise from the fact that the size of these constraints grows linearly with the network size. So it's proportional to the network size and could be exponential. To compute the output range could in fact be exponential in the network size. And so there's a lot of work on efficient encoding and solving subclasses of constraints. What we do here is take an alternate approach and try to see if we can reduce the network size and still obtain some good approximation of that input-output relation. So this is a work that appeared in Europe's 2019. So the broad goal is to reduce the network size for the purpose of safety analysis. That is, we want to construct a smaller network whose output range over approximates that of the given network. So we have this concrete system and we have this abstract system. And we want this abstract system to over approximate the concrete system. So recall that the neural network itself is a deterministic system in the sense that if you give a valuation to the input, there's a unique valuation at the output. And if we want a system that over approximates the behavior, then we need some notion of non-determinism in this abstract system. So we propose this new data structure that we call the interval neural networks, which are essentially like neural networks, but the weights and the biases are now intervals rather than just unique weights. And so at any node, given a input valuation, you might have a set of values rather than a single value. And the semantics is again very similar to a neural network, except that now you could choose any of the weights from the intervals. You could also interpret the input-output relation as the union of the input-output relations of a potentially infinite number of neural networks, which instantiate their weights with some weight from the corresponding intervals. So our broad approach for abstraction consists of first merging the neural network to construct this interval neural network, which over approximates, whose semantics over approximates that of the neural network. And then we want some way to verify this interval neural network. So we will extend the MILP-based encoding that people have developed for neural networks to the context of this interval neural networks. So let's look at the first step. So broadly, we partition the set of nodes into some number of sets, and we merge the nodes in those sets. This is similar to what you would do in predicate abstraction of a finite state system. So then we need to compute the weights. And somehow the weights need to ensure that we over approximate the neural network semantics. So here is a first try on computing the interval, weights on the abstract system. We could just take the interval hull of all the weights of the edges that are being merged in that particular partitioning scheme. So here is a concrete system. Let's say we merge these two nodes. So we end up with this abstract system where essentially the weight on the first edge is the interval hull of the two edges here. And similarly for the second edge. So suppose we start with an input of 1, we get an input, we get a value of 1 for the nodes in the hidden layer, and we get an output of 2. On the other hand, if we input 1 to the abstract system, we end up with a value of 1 at the output. So it doesn't seem like the abstract system over approximates the semantics of the concrete system. So the way we fix it is by noticing that we had the value of 1 for these hidden layer nodes, and this 2 was obtained by adding this 1 twice, whereas in the abstract system that 1 is only added once. So what we do is we scale this interval hull by a factor, which is equal to the number of nodes being merged in the source. And for this example, we then get a weight of 2, and we get an output of 2, which over approximates the concrete system. So this broad abstraction technique does work in general. So I'll not get into the details, but one way is to look at this whole abstraction as a left abstraction and a right abstraction, and followed by a right abstraction. And one of them actually requires the scaling, whereas the other doesn't. That's why we only scale based on the number of nodes being merged in the source rather than the target. And this abstraction is sound for any activation function that is continuous, so we can go beyond ReLUs. So that's sort of the first part. The second part is we end up with an interval neural network, and we need to verify it now. Recall that we had this big M encoding for which was used in encoding the input-output relation. And
so, Pavithra, just to interrupt, you have about 4 minutes.
I have about 4 minutes.
Yeah.
Okay.
I mean, you can take a couple of minutes more if you want, but
sure. I'll try to wrap up. Yeah. So so this big M encoding. So recall that these weights were constants in the neural network, and now we have an interval neural network, and these weights there's no unique weight on the edge, but rather an interval. And an easy way to encode this interval neural network semantics is by just treating this WI as a variable and adding the constraints of this lower and upper bound on the weights. But this would then lead to nonlinear constraints. What we observe is that we can in fact construct an equivalent set of linear constraints, where in this first formula where excess upper bounds this constraint, we replace the WIs with the lower bound values, and in the second constraint we replace them with the upper bound values, and it turns out that the two sets of constraints are exactly the same. So we can still be in the MILP formalism. So I will just give a quick overview of some experimental analysis that we did on this ACAS-XU benchmark. So on the x-axis, you see the number of abstract nodes. On the y-axis, you see different metrics. So the first one is the abstraction time and the encoding time, which of course increase, but they're not sort of the bottlenecks. And in this graph, you see the time that is taken by the MILP solver, and that increases quite drastically with the increase in the number of abstract nodes. On the other hand, the output range, that is the precision of the output, also increases quite quickly with the increase in the number of abstract nodes. That is, as the system gets closer and closer to the concrete, you get better and better precision. So, but you see three curves in each of the graphs. They correspond to running the system on multiple random partitions and looking at what was the minimum, maximum, and the average. And you see that there is a lot of difference between the minimum and the maximum, even for a fixed number of abstract nodes. And what that suggests is that we really need to look at some good partitions, not just the partition size, in order to get precise results. So now when we put this whole system into the closed loop, then we run into other challenges. Suppose that we wanted to do bounded verification, then in that big M encoding, we need to compute an M, which is an upper bound of the values that the neural networks can take in that K steps that we have fixed. And that could actually lead to issues with scalability. So we also consider an alternate approach where instead of doing a big M encoding, we rely on existing neural network verification techniques and decompose this INN verification problem to a neural network verification problem. So the broad idea is quite simple. We can think of the interval neural network as a lower neural network and an upper neural network, where the lower neural network has all the lower bound values and the upper neural network has all the upper bound values. And what we can see is that there's a lower and upper bound networks. If we take the interval hull of the outputs, it gives exactly what the INN would have given as the output. And this works as long as our input is a positive value. It turns out that it doesn't quite work for negative values. But in our system, the negative values only appear at the input layer, and in all the other intermediate layer, we have a ReLU function and we do have a positive value. But we can fix this issue with negative value by partitioning our input based on the sign of each component, and then appropriately choosing the upper and lower bound weights for that first layer. So we might have to solve the input-output, the output range analysis problem on exponentially many partitions for the input, for the upper and the lower neural networks. And that's going to be something that we need to address going forward. So yeah, I think just to conclude, what I presented is an abstraction-based approach, which which sort of complements the existing approaches in the sense that it could be used as a pre-processing step before applying other neural network verification techniques. However, we need to extend these neural network verification techniques to the interval neural network analysis. But this, I mean, we showed that this could potentially be done for certain techniques like these MILP-based encoding. And our experiments highlighted the trade-off between precision and computation time. And in particular, the precision could be affected by the particular choice of the partitions. And one of the things that we are doing is exploring different partitioning strategies based on a cigar-like framework. Yeah, so I'll conclude here. And this is a joint work with my students, Ratanlal and Zara. Thank you.
Thanks, Pavithra. So if you have any questions, please post them on the chat or feel free to ask them. So I'll start off. I assume you've shown that the abstraction is sound, but I'm a little worried about the lack of fan out. That you merged, say, to target the right merging, and as a result of that, you made the two inputs equal. And that actually, gives you behaviors that, that is, it restricts the behaviors in terms of missing some things that were in the original neural net.
So are you talking about this particular example?
I mean, yeah, for not this one, actually. I'm thinking about, let's say, you merge those two, and because of that, S01's output now is seen as equal by S1, the merging of S11 and S12. So you don't have a fan out here.
Mm-hmm. So you're concerned about the soundness of the abstraction technique?
That's right, yeah.
Okay. So so what, there is another way to view this whole merging, which is we can annotate the nodes by the number of nodes that were merged to obtain that particular node in any stage of the abstraction. And all we are doing is multiplying by that number of nodes that were merged in the abstraction. So what I want to say is that, yeah, the abstraction is sound, but there are certain issues with the abstraction in the sense that if you do a sequence of abstractions, you might not end up with the same abstraction depending on the sequence of partitions that you use to arrive at it.
I see.
But
so I mean, yeah. So you do kind of take into account the fan out issue though in the abstraction. You do,
yeah.
And by essentially memoizing the number of nodes you merge.
Yes.
Okay. Now, what partitioning heuristics actually work well?
So so there's no bound on the precision in particular, but we are exploring certain partitions based on some pi simulation like relations, which would sort of say which of these edges are close by and merged, which edges can be merged so that we can get a bound on the abstraction error.
Can you merge layers?
Yeah, so no, not in the one that we are looking at. Yeah, so that would, yeah, I mean, I think for that, we will need to rethink about the correctness if we were to merge different layers.
Okay, Mohammed has a question. Mohammed, feel free to ask it live. Okay, I'll ask it. Can you explain how the interval is selected for each weight and bias? How can you be sure that the end result remains correct?
Okay. So the way you, so let me look at this example. We are constructing the abstraction and we can think about it. So suppose I wanted to merge these two nodes and these two nodes. And I'm going to think of this whole merging process as happening in two steps. In the first step, I merge the nodes on the left, which is what I'm calling as left abstraction. And in that, I'm just going to take the interval hull of the corresponding weights on the edges. So for instance, when I merge these two nodes, the edge with weight 7 and the edge with weight 10 get merged. And the interval hull of those is 7 to 10. Okay, so what I'm going to do is I'm going to multiply that interval by 2 because I'm merging two nodes. And I need to do that correction to ensure soundness. But when I do the right abstraction, I don't need to do any more of this scaling. For instance, here I merge these two nodes, right? And in that process, I'm merging this interval 14 to 20 and 16 to 22. And the interval hull, which is essentially the convex hull of the two intervals, is 14 to 22. That's the weight on this edge. And so essentially what we can show is that whatever value appears here on this can actually be mimicked by some linear combination of these values. So the details of the proof are in this paper, or I mean, it might not be in the paper, but it's in the appendix of the paper, which I would be happy to share. But the abstraction procedure essentially is you look at, so in sum, what happens is if I'm merging these two nodes and these two nodes, I look at all the edges between this set of nodes and this set of nodes. I look at the interval hull of all the weights on the edges that are being merged. And then I multiply it by a factor, which is the number of nodes I'm merging in the incoming layer.
Okay, Supratik has a question.
Yeah, hi Pavithra, thanks for the nice talk. So I guess what's going on here is, kind of finding some kind of fine balance between precision and complexity of solving these constraints. So since you're using this to do output range analysis, I was wondering, how does this compare to, let us say, the deep poly kind of stuff, or how does this compare to Reluplex? I mean, you talked about MILP, so I was just wondering, how does using MILP compare in terms of the performance accuracy trade-off? But I guess it's just performance. It will be, I mean, if you solve the MILP, it will be exact. So how does it compare with respect to performance with Reluplex, let us say?
Sure. So I think I mentioned at some point that, yeah.
Oh, okay. Maybe
So I just briefly mentioned some related work, right? So yeah, we looked into Reluplex as well. And so the way I look at this abstraction approach is as a complementary approach to verifying any verification algorithm on neural networks, in the sense that one could use this abstraction to reduce the network size before applying the either a symbolic verification kind of method or other abstraction techniques as well. So we didn't quite compare it. So what we did was see how this could be used in conjunction with MILP to do the analysis. But coming back to your question, so we could also extend Reluplex to encode interval neural networks. We did talk to Guy Katz about that. So yeah, so you could use this as a first step in your overall verification algorithm, and then use either an MILP encoding or Reluplex to do the analysis on the interval neural network. So the main gain is that you will be doing the analysis on a smaller network, if that answers. So we haven't done a direct comparison of, because I mean, the main crux of the algorithm is the abstraction, and we just piggyback on existing verification algorithms.
But then how would you compare it with, let us say, deep poly, where you're relaxing the constraints at the values, you're not keeping them precisely, presumably to gain efficiency.
Okay.
Right. I mean, that's one kind of precision performance trade-off, and I guess you're doing another kind of precision performance trade-off.
Yeah.
So how do these two compare?
Okay, I'm going to step in here and put this discussion perhaps in a breakout room because we need to get to the break. So is that okay, Supratik?
Oh yeah, sure.
Okay, so thanks for beautiful talk, and if I'll set up breakout rooms. If the speakers can head off to the breakout rooms, we can continue the discussions there. So let me stop the recording after thanking Pavithra, and take care. Yeah, bye. Okay, it's my pleasure to introduce Professor P. Madhusudan, who's currently at the University of Illinois at Urbana-Champaign. I've known Madhu since I think he was a child. I used to visit him at math science, and I think that's where he got his PhD, and then he did a postdoc with Rajiv, and he's been on a tear at Illinois ever since. He's actually currently on sabbatical at San Diego. That's where he's speaking from, on automating logic reasoning for building verified software. Madhu.
Thank you. So I'm going to talk about automating logic reasoning for building verified software. And this is joint work with lots of people, but mainly two students, Lucas Pena and Aditya Murali at University of Illinois, and also collaboration with Christoph Luding at RVT Hub. So the way I look at automating logic reasoning for verifying programs is that I look at I think there are two different problems, right? One problem is you're given a program and a specification written by someone, and they would like you to verify it. And there's a lot of techniques over years for which we've developed. SV-Comp is a good benchmark and a competition that showcases some of these tools and results. But in most cases, these are very shallow specifications. For example, kind of assertions on the program variables in your program. The other aspect of program verification, which this talk is mostly about, is going to be on automated techniques to help programmers build verified software, which I think is slightly different in the emphasis it places on various aspects of the problem. So here we are more interested in program logics with verification support that we can provide for programmers. And, so more along the lines of Daphne or the Boogie pipeline, and work like Ironclad or Ironfleet, which essentially use, Boogie with SMT solving to build systems that are verified. And the specifications here are much richer. So you have mathematical Go structures like sequences of, let's say arrival of messages in a distributed system. You'd model it using very complex mathematical structures, and specifications are on them. And I think of this, the latter problem, as actually an AI problem, right? And I'm not sure the former problem is actually solvable, but I think the latter problem is solvable in the sense that there is an existential proof that it's solvable, namely humans can solve it, right? Most of these things are things that humans can do. When they build their software, they are able to, kind of verify them in many ways. So I think of it as really an AI problem. We're trying to automate the reasoning that is done by programmers today. So here's the hypothesis, which I think is interesting, is automated techniques can go a long way in helping programmers build verified programs against rich functional specifications, automating most routine tasks in verification, right? And so despite a lot of research, I think this hypothesis has not been really tested. Most work I know on verifying, building verified software, we use theorem provers such as Coq, where, little of the automation that I'm talking about in terms of, automated logic engines that like SMT solvers have been used in such pipelines, except for some work like Ironclad and Ironfleet. So there is this anecdotal evidence that, the Daphne Boogie pipeline toolchain, SMT toolchain, is enough to get verification done with very little annotations, but still it's not vetted well, right? And I'll talk about effort we've been trying to do which suggests that it may not actually be true, and lots more work is actually required. So the theory here is identifying the automation that is needed in a verification pipeline of this sort, including programming logics, program logics, validity reasoning for verification conditions, and also finding inductive invariance. And in practice, how do we use these automation to actually build realistic, large, verified software? So I'll talk about both experiences a little bit. So my work is focused on the theory domain on two aspects. One is for validity reasoning. The main bit here is that I don't believe quantifier reasoning is enough for proving software. It is, if you take any realistic application and try to prove it, quantifier reasoning is just simply not enough. And in particular, data structures and rich specifications require quantified logics and also recursive definitions to deal with finite tree structures. So you need some kind of recursive definitions or least fixed points in your logic. So even first order logic with quantifiers is not good enough. So here we've been working mainly on automating first order logic with least fixed points, including I'll talk about a Nelson-Open like result for quantified logics. The second one is automating techniques for finding inductive invariance. And here I've found in the world of building verified software, the black box techniques kind of work the best. And I've been working on this ICE learning model, but I won't talk about that today. And in practice, I'm going to talk a little bit about, in the end of my talk, about a verified blockchain that we tried to build and the challenges we found there. So the first thing is I want to tell you about is logics with quantifier and recursion. You really need this, not only to express properties about data structures, but also to express the specification itself. And the specifications are complex. They involve mathematical things like sequences, sets, pure functions, arithmetic, and all kinds of other things that you really need quantifiers for. And you could argue, logics with quantified with quantifiers are actually undecidable, and you could imagine that you could say maybe we can find decidable and powerful quantified logics, right? That will be enough to prove software correct, but that's been a futile attempt. I've worked on it for years and I've given up. I don't think there are such logics that are decidable and yet powerful enough. I think we have to embrace undecidability. So, but decidability is not the goal, right? The automation is the goal, not decidability. And I think it's important to give up decidability and embrace automation. So the grand plan, which I've been working on for several years, is to establish first order logic with recursive definitions, or first order logic with least fixed points, depending on what you're more comfortable with, as an automated program logic. I'm sure you've forgotten all your logic basics. So just to remind you, first order logic, is undecidable, but it admits complete procedures, which are not decision procedures. And first order logic with recursive definitions is not even complete. So there is no hope for completeness. But most proofs using recursive definitions for first order logic are based on induction, and they're typically sufficient. So even though you don't have a complete proof system, a proof system that supports induction is typically sufficient for most theorems. So the idea here is to build for first order logic is to build complete procedures that also scale in practice, and for first order logic with least fixed points to build practical procedures that are relatively complete in the sense that two induction proofs. And also from the world of separation logic and so on, we know that we need frame reasoning in any program logic. So we've endowed first order logic with least fixed point with frame reasoning. And we can then, essentially reason very similar to separation logic in this world of first order logic with least fixed points. And ultimately, the ultimate goal is to, kind of provide people not just with SMT solvers for quantifier-free logics, but, full-fledged solvers that can handle, first order logic with least fixed point and maybe even higher order logics. So we've been working on this for quite a while. And it started out with some heuristics that we discovered. And it's done by lots of people, others as well, that there is a particular heuristic of unfolding recursive definitions followed by abstraction that seems to work very well for reasoning with data structures. And we found that we could take fragments of separation logic, reasonably expressive fragments, and model it as in first order logic with least fixed points. And we also looked at this heuristic and looked at why it was actually working and found a very good theory, very nice theory on it, which I'll talk about briefly. But we also extended this logic to frame reasoning. So we have this logic called frame logic, which is first order logic with frames as explicit operators that allow you to do frame reasoning much better. So I want to give you a glimpse of what these things look like. So why are first order logic with recursive definitions useful, it turns out that most things about data structures you can define in this way, right? So you can model pointers using unary functions and start defining recursive data structures like lists or trees. And this tree definition is very similar to how separation logic would define it, namely that X points to a tree if X is nil, or you have a left and a right tree which are disjoint. And you can define the heaplet or the associated with the tree also as a recursive definition, which is given below. And in this way, you can actually capture most interesting properties about data structures. So turning to reasoning, we found that this heuristic works very well in practice. Is that it's an extremely simple heuristic. It says unfold your recursive definitions and do frame reasoning on only the ground terms that you find in your formula. Then throw away the recursive definitions entirely and just treat them as uninterpreted. And you need a few recursive induction axioms, properties about data structures that are inductive. These are crucial. But once you combine these three, using just an SMT solver, you can actually reason with first order logic with least fixed point definitions, and it works really well. This is also similar to how Ranjit Jala works on liquid types. Checking is done using a very similar heuristics. And again, there it works extremely well. And so we wanted to understand this, and over the years, we have mostly resolved this question. And I'd like to tell you how it got resolved. So how do you do first order reasoning in general, right? We know by Gödel's completeness theorem that there is a sound and complete proof system, but actually there is, Gilmore in 60 actually proposed a complete method for first order logic based on Herbrand's theorem, reducing it to propositional reasoning. It turns out that we can go a step above that and say, instead of propositional reasoning, we can reduce it to SMT solving, or you don't need to reduce it all the way down to propositional reasoning, but you can reduce it to SMT solving. So here's the rough algorithm. You take a first order formula, you have to check for validity, you negate it, and you Coulombize it to get a universally quantified formula. And then what you do is you systematically instantiate the quantifiers. So if you have for all x phi, you take your variables and instantiate it with ground terms. If you instantiate it systematically, you are bound to prove the theorem, right? This is a simple consequence of Herbrand's theorem, that you will find a proof. Okay, but the idea is that when you instantiate the variables with ground terms, you are in a decidable theory, because this is the theory of uninterpreted functions. And therefore you have a decision procedure for it, and you can use that to automate reasoning. This is not a decision procedure. This is only a complete procedure, right? If the theorem is valid, you're guaranteed that at some point, some amount of term instantiation will result in an unsatisfiable formula. So it turns out that this holds for formula-based quantify instantiation as well. So this is a heuristic which is slightly different in that you don't instantiate with all possible terms, but rather what you do is instantiate only terms that occur in the formula. And it turns out that even if you do that, you do get completeness, right? And we have this fairly nice result, and I'd like to tell you about it. But we have essentially a Nelson-Oppen-like result, which says that the similar quantify instantiation will work even in the presence of background theories. So in particular, there is this thing called the safe fragment. I'm going to skip over some details, but it turns out there's a notion of a safe fragment for which it turns out that you can actually combine theories, and you can just, by doing instantiation in the foreground universe, you can reduce it to reasoning with SMT solvers. And this gives you a complete decision procedure for first order logic, right? Even in the presence of these background theories that you have decision procedures for. So it turns out that, I'm going to skip one more slide because I'm running out of time, but it turns out that modeling heaps turns out to be in the safe fragment. So it turns out that if you model in the foreground universe, heap locations, and you have functions like length take you from the foreground to the background, and if you have only functions which go from the foreground to the background, it turns out it's in the safe fragment that we define, and therefore you actually get a complete procedure in this universe, right? So this is our explanation as to why this heuristic works incredibly well in practice, is really because that it's a complete procedure. But turning to first order logic with least fixed points, it's much harder. But you can think of a general proof in first order logic with least fixed points using induction as follows. So first you state a lemma about, you use a set of lemmas. The lemma is really like an induction hypothesis. And then you have to prove the induction step of the lemma, which we generalize into something called a prefix point. So you give a first order proof of the induction step, right? So in the induction step, you're doing only first order reasoning. You're ignoring any least fixed point operators at that point. You're giving only first order reasoning, and you're establishing that the theorem holds by induction. Now, the fact that phi1 holds because you prove the induction step uses the least fixed point semantics. But you can split your proof into essentially first order proofs punctuated by these induction hypotheses about various theorems. And so what you can think about the proof is really you have to synthesize these inductive hypotheses and just do pure first order reasoning. And so this becomes a synthesis plus deduction kind of problem, right? And we have built, this is ongoing work. We're building counterexample driven schemes to actually find such lemmas and be able to prove theorems using for first order logic with least fixed points. We're also looking beyond FO plus LFP. So we're looking at algebraic data types, typically used in functional programming, and also higher order functions. And in particular, as I said, Ranjit uses this kind of technique, and we are trying to find a similar theory that explains the efficacy in that world. And it looks like it's possible. So we have some results now that establish that there are similar safe fragments there for which the technique is complete. So so this idea of using quantify instantiation, I think, is very interesting. In fact, I have in my slides, I have some lecture notes. I now have
Madhu, can you wrap up in 3 minutes?
Yeah. Yes. I have essentially a textbook written of sorts, which essentially proves Gödel's theorem using quantify instantiation. So it's a way you can, I encourage you to check it out and maybe use in your courses. It's a way to teach Gödel's completeness theorem using SMT solvers, right? By just reducing first order reasoning by a sequence of reductions to SMT, right? So let me move to the practice bit. I also wanted to check out how close we are to reality, and I wanted to build a verified blockchain because blockchains are cool. Applying natural proofs that we have done, we thought we could test this hypothesis. So we decided to do a verified blockchain and a Bitcoin system, and this is work at FMCAD 19. So we decided to go and build this blockchain consensus and integrity verified system, starting with what I would call a mixed method. So in the beginning, you start with a Coq model, where you have a very abstract model, which is proved to have certain nice properties. It's a blockchain protocol. And then we continuously refine it. So we first do some refinements in Coq itself, and then we translate it to Daphne, and using Daphne contracts, we imbibe the specification from Coq, and then refine the Daphne code slowly to write imperative code and then to do performance. And finally, we put in a shim layer for talking to an actual network and so on. And we finally end up with a distributed system. And I thought this will be successful because of the success of Ironclad and Iron Fleet. But there are some fundamental differences between this work and Ironclad and Iron Fleet. In particular, blockchain is a very intensive computational operation, and getting performance is extremely hard here. And we ran into all kinds of problems here. In particular, I think we bit off way more than we could chew. And we did not, end up with a fully verified system. It was performance was gotten with some cuts to verification. We didn't, we weren't able to entirely refine it, mainly because the original model that we started out with was not computationally efficient. And secondly, the whole chain was too complex because there were lack of tools. So when we need to do a refinement for computational purposes, it wasn't quite the same refinement. It wasn't a valid refinement. And secondly, this whole refinement is not very well understood. In particular, we could not add concurrency at each node of the blockchain system and the end, and that hugely impacted performance. So the key takeaways we had on this was that Daphne needs, to support first-order logic with least fixed point reasoning much better, perhaps using natural proofs. It was way too hard to use Daphne. Then the second thing is refinement from models to code is actually quite a mess. People don't quite know how to do it. The work presented in systems is mostly on small cases, on particular cases that happen to work, but I don't think it is a general technique. And I think a lot of theory is needed for establishing distributed refinement as a reasonable scientific technique to build programs. So I'll conclude. So roughly speaking, I want to replace SMT solvers with first order and maybe even higher order logic automated engines. We have some work for first order logic and least fixed point, which suggests that this is indeed possible. But we really need program verification engines that, kind of take these techniques and imbibe them. And I'm not entirely sure who's going to do that. Who's going to take Daphne and imbibe, put on all these techniques inside Daphne. And finally, distributed and concurrent refinement is far from clear. So I would really love to test this hypothesis as to, whether automated techniques can actually help in building verified software. And I think there's a lot of work to be done here. Thank you.
Thanks, Madhu. You've covered a lot of ground in this and raised a number of issues. So one thing actually I should mention is that the system and methodology you describe is I think new and interesting, but some of the points you made are actually well known from way back. So the unfolding of recursive definitions and then the treating of those function symbols as uninterpreted is already the case in the Boimo theorem prover from the 70s. And then the reduction to SMT is the principle that PVS is based on. And so, that's, it worked powerfully. And already in the 90s, I believe that we approached feasibility in terms of a qualified person being able to develop verified code at a clip that would be comparable to unverified code. I think the challenge, the gap really was this idea of actually reducing the level of qualification needed to drive these things. And that's, I still see a concern out here. And I mean, the methodology you've described would still pose challenges for the non-expert. What do you think?
Yeah, I think the new results here are basically the safe fragment for which it's complete. And I think empirically we find that, you know, this technique works pretty much only in that domain. So I'm not sure. So whether it'll work otherwise. So if you just took arrays and you know, general logic, I think it just doesn't work. The quantified instantiation doesn't work well enough. So you know, I think it has to be these, though quantified instantiation looks like it's a reasonable thing, it's not. I mean, once you do it, it kind of blows up on your face. So you do have to use it very carefully. I think the safe fragment gives you at least some, you know, intuition of when it might work well. Yeah, so there was questions, ACL2. Yes, so a lot of work has been done. Also the Boy-Moore theorem, a lot of work has been done on what I would call algebraic data types. You know, there's a lot of work, or term algebras, there's been a lot of work on doing something very similar. I think, again, the counterexample based lemma synthesis, as far as I know, is new. It seems to work well. And also, you know, this idea of using, for imperative programs, it's not clear that they're not algebraic data types. And you have this crazy functional world where you have least fixed point definitions, where I don't think the earlier techniques applied. Sorry, you're muted, Shankar.
Do you see Dave Norman's question?
Yeah, so Dave, would you like to ask, or I can just read it also, but.
It's kind of a minor point, but I very much appreciate this line of work and the great results that you've been obtaining here. My question was about a specific technique. One of the ways of sort of dodging the need for these fixed point reasoning is sometimes people just instrument code, so you're sort of tracking enough information that, in fact, I could prove that I've got an inductively defined property, but the VCs won't require any inductive reasoning. I'm just curious if you see that as part of the.
Yes. So yeah, so people use ghost code to keep track of this invariant so that it becomes local. I presume that's roughly what you're referring to. Yes, so you know, that is what we'd like to replace with, where you know, of course, one could give some indication of how the invariant is maintained, but you would like the proof to kind of go through much more automatically than how Daphne does currently. You do most of the reasoning today when you write this kind of ghost code. But I agree that that's how Daphne gets it done today.
So Martin had a question about you know, whether by SMT you do mean just the quantifier-free fragments.
Yes, I do mean only the quantifier-free fragments. Yes.
Okay, then Andre's question is, would the completeness of resolution-based procedure directly imply the completeness of systematic formula-based instantiation? I think you said that the FO plus LFP is actually not complete in that sense, right?
Right. I think, but for the first order logic, the formula-based instantiation, would it imply? I am not sure. It could. That's an interesting thought. I have to check that.
Right.
I don't know if it's. It is not it's not a hard proof. It's a very simple proof. I just wanted to emphasize it, but it's in our paper. It's not even you know, it's not even explained. It's a very simple consequence. Yeah.
It's basically Koenig's lemma, right?
No, this is formula-based instantiation. You instantiate only on the terms that are occur in the formula.
Yeah, that's true. Yeah, but it's but the general completeness argument, you know, can follow from Koenig's lemma. So okay, then Phil Wadler asks if the soundness and completeness also apply to constructive logics. Does moving to constructive logic make the problem easier or harder?
Yeah, I don't know. So we are just moving into the ADT world, and we would like to look at constructive logic here, but I don't know whether it becomes easier or harder. It's a very good question. I really don't know.
So
I would.
one issue here is that the SMT solvers are actually classical, not constructive
Yes.
on most theories.
Right, but the way we do induction should be easier for constructive logic at the same time. So I think there is some evidence that it might be easier, but I'm not sure.
Okay, so I'll take maybe two more questions. One is a suggestion from David Norman about using Viper. I think good suggestion. And then the next one's from Mohammed on blockchain. Did you get any? Did you interact with implementers of any specific?
Yeah, so the blockchain system was built in collaboration with the systems group, which was constantly looking at. They were building the system, and we were proving it. They were very unhappy with the how their hands were tied, because in order to be a refinement, they wanted to, let's say, cache a result about the blockchain, and just caching a result about a blockchain and then reusing it, assuming that the blockchain hasn't changed and then whether it's changed or not, is not a refinement. And they were very surprised and about how much their hands were tied. And I think they did get the whole idea at the end. Now, the results were not strong enough, right? So we did not publish this in a systems conference like OSDI, but because it's the end system is not really performant. We had to, with respect to a reference implementation, it was just not strong enough, and we just didn't have the, this was already a year and a half, so we didn't have the, gumption, especially without all these tools, to go back and refine, start from scratch. I think we can do much better now. If we start with Cork with a performance model in mind, we can do much better. But we just lost steam, I think, at that point.
Anyway, thanks, Madhu, for a really stimulating and provocative talk. There's much to discuss out there, and hope we'll continue the dialogue. But before I hand over the chairmanship duties to Moshe, it's my pleasure to thank everybody involved in putting this workshop together, especially thank the Newton Institute folks who, you met Gemma and Paul, but there are a number of other people working behind the scenes, Megan and Samantha and Dan and various others, to make things run smoothly and actually, be very cooperative and flexible about many issues. So I'd like to thank them. I'd like to thank the organizers from our end, especially Azadeh and Philippa, who conceptualized the whole thing and put it together, but with consultancy from the others who've been part of this. So the workshop is actually a prelude to a program at the Newton Institute in 2022. So I hope you'll look for it. So with this, I'll hand it over to Moshe.
Thank you, Shankar. So I hope today I'm hopping on and off between multiple things, but I couldn't pass an opportunity to introduce both Tom Henzinger and Rajiv Allur. So Rajiv and I did some work together when he was a PhD student, which is enough for me to claim him very proudly as partly as my PhD student. And he has done many great things since then. And I would say just one thing, he has a paper with over almost 9,000 citations. The paper on the theory of timed automata has close to 9,000 citations, which is just mind-blowing, because there are many people who would love to have total citation in that region. So it's been one of the most impactful paper in formal methods of the past generation. And he's going to tell us today about formal verification for safe autonomy.
Thank you, Moshe, for that kind introduction. Also, thanks to Shankar and Philippa and Azadeh for organizing this great workshop. We are all, professionally isolated, but this gave great opportunity to listen to some of the very cool things that are happening now. And hopefully next year we can get together physically and interact better. So I'm going to focus on safe autonomy. So, switching of gears from what Madhu just talked about, but it's quite related to a number of talks in this workshop earlier, like Martin Bechev and Marta talked about it, and today Sanjit and Pavithra also talked about it. So the problem that I want to focus on is the problem related to design of control systems. So you have a physical plant, like maybe a car, and you want to design a controller that's measuring the plant through sensors and then wants to influence the behavior of the plant by sending control inputs to the actuators of the plant. And the outline of my talk is, first, I'm going to tell you about why would one want to use machine learning for designing controllers? In particular, why would you want to implement a controller as a neural network in some contexts? Having designed a controller using, say, the state-of-the-art, say, reinforcement learning algorithm, why would anyone want the help of formal methods community, or the people in this workshop to verify it? And I'll tell you about some of the work that we have recently done on developing such verification methods. So keeping with the theme of this workshop, well, the title was from theory to practice. So actually, I'm going to go the other way, and I'm going to start with some practice and focus this whole talk using a case study, which is related to this F-110 autonomous racing car. So what is this racing car? So here is a little video of this car. Actually, it's going through these corridors. This is right outside my office. So this platform was built in the Precise Lab at Penn, and it started off as a platform for educational purposes. So it is I mean, it's an actual car, but it's the 10th of the size of a real car, and has sensors and has LiDAR readings. And so the LiDAR readings give you measurements of what's happening, what the world around you. And then the problem is you have to map the world and then decide decide on navigation strategies, how fast you go and when to turn and so on. Right? So if you want to teach students about design of embedded systems, integration of perception and control and sensing and low-level C programming, this is a great platform. Costs about $400, and in the last few years, it's become super popular as an educational tool. Lots of embedded systems courses in control designed around it. And this website, f110.org, actually gives you all the information about this. And of course, compared to the challenges in autonomous driving, this is a much simpler problem. But compared to the techniques where formal methods have been applied, as we will see, I think this is really what we have done is pretty much state of the art. In particular, it's not in simulation. It's the verified, the controller that we verified is the one that actually that's running on, on this car that you see here. So let's start with, how does one go about thinking about, control in this setting? So the car can be modeled using 5 state variables. So you have 2-dimensional position, then the linear velocity, angular velocity, and orientation. And there are 2 control inputs, the throttle, which can change the speed, and the steering, which can change the direction. And then, one can model the dynamics of the car using some textbook models. Like there is the standard bicycle model, which is commonly used in robotic setting for plant. Right? So what's the control design problem here? So well, we suppose we know the current state of the car, which is this 5-dimensional state, and what the control design problem is to determine the throttle and the steering. And the goal is to make sure that the car does not crash, so it doesn't collide into the corridors, but you can sense the world around you only through these LiDAR sensors. So LiDAR is like this latest technology. It's fast developing, but it's very cheap. And in this particular context, like in this specific hardware, you have 1080 rays which span this 270 degrees. So so in each direction, this LiDAR array tells you within up to 10 meters whether there is an obstacle. So for example, the reading says 3 meters. That means the ray could travel only up to 3 meters and there is an obstacle. So you get this vector of readings, and then you need to figure out, you need to do a bit of mapping and say, okay, what the world around you looks like, and then use it to decide what to do, right? So
do you get a reading for each ray?
Yes, so you get basically, it's an array of 1080 things, but it's noisy. So that actually complicates the problem that, so in some direction, maybe you don't have a reading because, that ray didn't reflect properly or something like that. Yeah, so there's a bit of noise in this vector. So I think in this workshop, we heard a number of talks about how to verify neural networks. For example, Martin Vechev was talking about abstract interpretation techniques to show some input-output behavior of neural networks. So one challenge in those settings is what's the specification? When we go to closed-loop systems, so there are other challenges, but this particular challenge goes away about specifications, because for the closed-loop systems, the requirements are very clear. For this car, we want to avoid collisions. It should follow the racing path in the highways, and it should minimize the finish time. Oh, actually, I forgot to mention one cool thing about this F110 car. There is this annual competition. Actually, now it's held multiple times in a variety of conferences like Embedded Systems Week and CPS Week. And the goal of the competition is really racing. So the different student teams basically program this car, and they don't know the track in advance. And upon deployment, the car is dropped onto this track, and whoever wins, it's really a race. Whoever finishes first wins, and of course, whoever collides is disqualified. So you have very nice qualitative and quantitative specs in this setting. So why do learning, right? So if you describe this problem to a control engineer, then what they would probably try to do is to split it into levels. So you first take these LiDAR readings and make up a map of the world. And then once you have mapped, then there are lots of techniques in planning and control and robotics that could be used. The benefit of trying to train a neural network here is that since the LiDAR is kind of noisy, and then it's this this array of complicated readings, writing this code is kind of cumbersome. And so mapping the world from LiDAR readings is not a well understood problem. So once you have a map, then how to design control is well understood. So the temptation to use neural network is you design a neural network where the input is this vector of 1080 readings from different directions, and the output is going to be the two control outputs, which is the steering and the speed, right? So to do this, then you don't have to do kind of build a model, and what you get is really the neural network, so that can be evaluated very fast, because if you write complicated code, this is going to run in real time on the car, and that could slow down the car, right? So that's kind of the benefit of using neural network. But of course, you need training data, which could be obtained using simulation. But once you train it, then what happens? Well, you don't have a guarantee of safety, because depending on the algorithm that you use to train, maybe you have some statistical guarantee, but who knows about the distribution of actually the the tracks that appear in practice, right? So when you deploy the car. So a quick reminder about neural networks, and we saw this reminder in various talks. But this is an example of a neural network where you have an input layer, a number of hidden layers and outputs. And a typical neuron is basically a non-linear function of the neurons from the previous layer. And so this ReLU is one example of a neuron. And the behavior is determined by the weights. And during the training, if you are using, say, reinforcement learning, these weights get adjusted depending on the simulation data that you use. So one thing to point out is this is going to be a highly nonlinear function. And that's actually a challenge, particularly for automated verification techniques like state space exploration or model checking type techniques. So what we did was, well, we trained the neural network. We had to simplify the problem because for the neural network that we obtained, we wanted to verify it. So we reduced the number of LiDAR rays from 1080 to 21. But actually, the card that you saw is that it runs on this trained neural network. So there is some redundancy in the hardware that's available. And we kept the speed fixed, and so the only input was the change in the direction, right? And so as you do in simulations, you fix a particular hallway geometry, you fix a particular initial state, you see how the current neural network works, and use that to decide on the reward, and then you keep training till you are happy with your results, right? And the result was a neural network with 21 inputs. There are 2 layers, each with 64 neurons. So so when people talk about deep neural networks used in, let's say, perception, they are much bigger. But in this particular case, this was good enough, and this is what our verification tool could handle. So at this point, if you well, this is not needed for this workshop, but I think as we want to sell our techniques to the outside world also. And AI is, it's exploding. I mean, it's probably the size of AI community is 1,000 times the size of the formal methods community. And we do want to convince them that verification has something to contribute, right? And so this is kind of an argument for that when people talk about safe AI in the machine learning community, they are focused on designing machine learning algorithms that integrate some symbolic constraints during the optimization phase, right? During training, right? The problem is, if you think about the history of software, complex software, right? So say, pick your favorite software development company. There would be a team that's designing the software, and there would be a team that's in charge of verification and validation. So going forward, even though you improve your machine learning algorithms to maybe get neural networks with better guarantees, there would still be a verification team, and we do need to provide these verification, validation, or testing engineers with tools that are independent of the ones that have been used during the training phase to do the traditional verification type of work, right? But of course, now they have to verify systems with these neural networks, right? So in this setting, with the current technology in machine learning algorithms, you actually don't get any good guarantees about safety. And in this case, it would be absence of collisions. And what we could hope to do using symbolic techniques is to verify maybe safety for a range of initial conditions, right? And as I mentioned, these LiDAR readings have noise, so we could model them as non-deterministic input and put some bounds on the range of what LiDARs would return. And then verify that under all possible scenarios, there is no collision. So that's our safety verification problem. So I have I have a trained neural network for the controller. I have a hybrid systems model for the plant. So actually, if you think about the dynamics of the car, it uses differential equations. So that's where the work done in hybrid systems community within the formal methods community comes into play. And then the safety property in this case is clear that that the car doesn't collide, right? So since we already have a plant model which involves differential equations and is a hybrid systems model, our thought was, let's try to adopt existing symbolic state space exploration techniques that have been developed for hybrid systems over the last, say, almost 30 years now, to apply it to this problem, right? So this is like one slide summary of how reach set computation for hybrid systems looks like. So you have some initial states and you want to design a post or an image computation step and apply it repeatedly to check whether an unsafe state is reachable or not. When the dynamics is modeled using differential equations, even when the initial set is nice, let's say a rectangle in 2 dimensions, the set of reachable states has a very complicated shapes. And so what the hybrid systems community has done over last 2 decades is developed a variety of techniques using, say, flow pipes and zonotopes and Taylor models to over approximate this set of reachable states. And one of these state-of-the-art tools is FlowStar at the University of Colorado, and that's the one that we use. So now, so the challenge now is how do we incorporate this neural network-based controller? So the tool that we currently have works with sigmoidal activation functions. And this is in 1 dimension, this is what a sigmoidal looks like. So sigma of x is 1/1 plus e to the power minus x, and this plot kind of suggests it. And so the key symbolic computation problem is, if I told you that x is in some set I, how would we compute an over approximation of the set of the possible outputs, right? But just based on this curve and what we were talking about in the context of hybrid systems, you can see the similarity. And I don't have time to go through the details, but the technique that we use is approximating reachable sets using Taylor models. And so basically any function can be approximated with looking at the Taylor series, and you along the way you can also compute worst case error bounds. And a number of hybrid systems verification tools, including this tool called FlowStar by Sriram Sankarnarayan's group at Colorado, use it. So we build on these techniques. And here are some papers which describe the tool that we have built here at Penn called VSOW, which focuses on extending this technology to deal with neural networks. So what's the outcome? So well, the deep neural network that I described earlier, that that we trained for this car. Actually, then we deploy it on the car, and that seems to work. And then we actually verify it also. As it turns out, it's only for the right turn. In fact, the learning was also for the right turn. Actually, the video that you saw, well, the car was always taking right turns, and the verification is also just for that, right? But still, I think it's interesting, because if you think about the case studies that people have done with hybrid systems tools, this is still, I think, pretty impressive. And also, it's a real system. And as you can see from these equations, there's lots of very complex equations. So there are lots of new challenges. So let me tell you briefly, like in 2 minutes, about one, which is interesting because this workshop started with Tony Ho's talk. And what we really do here is use some basic ideas from pre-post conditions. And what we want to do is to design and verify this controller that works for all possible corridors, right? And not just for the right turn. So one way to think about this is you can model the collection of all possible corridors as a non-deterministic hybrid automaton, where different modes correspond to different maneuvers, like go straight, turn right, turn left, sharp left, and sharp right. So we use these 5 maneuvers. And this actually helps in learning compositionally. Actually, those of you who have worked with reinforcement learning know that you need lots and lots of data, and training these neural networks is a nightmare. And even for this car, it's not possible if you want to train it for all possible corridors. So this compositional approach actually helps with learning also, where you learn the controller separately for each mode, and you have a mode predictor that predicts the current mode and that you learn separately. And then you can compositionally verify that for each mode, the controller is safe. But the key new thing, or kind of the challenge here, is that as you finish the right turn, you will end up in some state, right? And the state is this complex 5-dimensional vector. And you want to make sure that the set of states where you end up in matches with the initial condition for the next mode. So maybe after the right turn, you're going to make a sharp left or something like that. And the sharp left works for some set of initial conditions. So you can now think of this as designing pre-post conditions for these modes, synthesizing them so that the post of one matches or is a subset of the pre of the next one. And you want, during learning, so you want to do this integrated learning and synthesis and verification, because during learning, you want to make sure that the car ends up in the post condition of the current mode. So you need to set up your reward function so that you get penalized if you don't end up in the post condition. And you don't know this pre and post conditions a priori, so you want to synthesize them. In fact, this is very related to invariant synthesis problem. And actually, I'm glad that Madhu gave the previous talk, because we used a technique that his group had developed on this implication counterexamples. Because since we are synthesizing these pre-post conditions simultaneously, the counterexamples actually turn out to be implication counterexamples. So that worked out quite nicely. So this is a kind of work in progress, and what we can well, it's under submission, and what we can actually prove is that for all possible combinations of corridors, the car works. So let me wrap up here. So the problem here is how to verify safety of closed loop systems with neural network controllers. And the great thing about this problem is that it's really of interest to communities outside formal methods. So like, safe AI is like such a big buzzword. And there is, I think, well, I think I don't need to convince you that that's really an important problem. From a verification perspective, this, I think, conceptually also it's very intriguing, because if you look at a big neural network, there is no modular compositional structure. There is no notion of a lemma there. Like you can't prove a property of kind of a subnetwork. So that's, so, I mean, the way we verify properties of complex software is by breaking it into pieces. It's not clear how one would go about proving properties of these neural networks in a modular fashion. I described 2 ideas for solutions, one using symbolic reachability computation, and some compositionality where the control task was broken up into a sequence of subtasks. This is joint work with number of collaborators listed here. The VeriSig tool is available here, and this work was supported by DARPA and ONR. Let me stop here and take questions. So thank you very much for listening. I know this is kind of Friday evening for all you folks in Europe. So yeah, thank you for your attention.
Thank you, Rajiv. Could you stop sharing so we can see everyone? So I'll take the first question. So 5 years ago, there was the noise from the industry was that the autonomous vehicles are just about to arrive. We should just expect them to roll out any minute now. And now I think that just last week, I think Elon Musk says, well, maybe it's a bit more difficult than we thought. What's your take on that?
Well, I think well, I mean, I'm going. My take is as a verification researcher, right? So there are some maneuvers. So, for example, lane tracking or lane merging, right? So, these features are there already, or or those companies that who haven't deployed these yet, they are in the process of deploying those, right? So, I think so. So that's, so those are features of autonomous driving. And in fact, those features are small enough that are focused enough that we can also address them scientifically. So that's kind of a win-win situation, right? Because
actually, lane merging, people discovered that it's more difficult. If you take an AV to ask him to automatically to lane merge, you'll never succeed, because partly we are relying on human judgment that we can be a little aggressive, and the other driver will respond in kind. In fact, sometimes they don't respond appropriately, and then there is an accident. But you kind of blink and sometimes put your hand out, and you go out there taking a chance, knowing that they will slow down. But if you just try to do it mechanically, and it's not clear how you factor in this our social intelligence there, people discover it's sometimes impossible to merge automatically.
Yeah. But so so I guess so the buzzword there is a human-robot interaction, and there is a lot of interesting work happening on how to build models of other vehicles. But again, these are mental models, not of like human intelligence, just in the context of lane merging, right? What's the information, or what level of abstraction you need to model the cars around you, right? Which may be autonomous or may not be, right? Yeah, and I think that's plausible. I mean, maybe I think the and also people, there is simulation data available, tons of simulation data. You can try to extract models from that, right? Yeah.
Madhu, you have a question?
Yeah, but did Mohammed have a question already?
I'm sorry, did I miss a question?
I just
there?
don't want to, yeah.
Yeah.
Okay, so so the question is, what does one do if the neural network?
Yeah, that's my question. Is that if you found an over-approximation and it finds it not safe? I mean, you were lucky in some sense that it was safe, but if it was not safe, what would you do?
Oh, in this case, we were also training the neural network, so it's actually in a loop. So if it's not safe, you get a simulation. It's basically a simulation trajectory which you feed in as training data for the learning algorithm. Yeah, what happens? But that's a good question. So what happens if the verification team is different from the design team? And then yeah, that's yeah. I don't know the best way there. So yeah, but let me read.
Muhammad, there's a question. Muhammad, you want to ask your question?
Yeah. So
you have two machines. Turn off one of them.
Or I can read it.
Can you hear me?
Yeah. Okay.
Okay. So my question was about your, as you mentioned that formal verification basically needs many simplifications for when we are modeling the practical systems. And specifically, I'm interested in knowing that how do you ensure that the formal model actually still faithfully represents the real system or the practical system that you are verifying?
Well, I mean, it's a great question. So this sim to real gap, it's that's it's kind of a sub area in control. The gap between the simulation models and the real the real world. But so okay, so in this context, well, the model of the car. So by now people understand the car model is actually pretty good. I think the challenge here is the model of the LiDAR. And as far as I know, there are no good models of errors in LiDAR. So the one that we built could be way off. So it's an opportunity for future work. So I think, but LiDARs are becoming more and more popular. And if there are better models of the actual errors that LiDARs make, that would help, right? But this question is not just about verification. I mean, people have to do simulations, testing, a variety, or even training for these neural networks. So this is a problem of more general interest, right? Yeah. So,
okay, I think it's late in the UK. It's time for people to go to dinner. I'm looking at the face of some hungry people.
well,
So,
I see a number of questions here, so I don't know.
Is there any last question?
Well, if I may ask one, thanks for the talk, Rajiv. I mean, the obvious question from me, do you see any role in that particular kind of setting, for runtime shielding, or as it has been called?
Oh, definitely. Actually, yeah. I mean, I think shielding is, there's a lot of work going on about shielding, because actually, and that could address the question that we had from Madhu, that what happens if the neural network is found to be not safe. So you could have, so I think one solution people have advocated, and I think it's appealing, is you design one controller which is kind of safe, is very conservative, and but has using traditional techniques, and then the neural network is the one that you use during runtime. But if you find some violation, but it needs to be predictive. So you predict that you're too close to the unsafe set or something like that, and then you switch to the safe version. Yeah, that's that would be a great application for runtime verification. But yeah, people are already working on that. Yeah.
Thank you, Rajiv. Thank you, Rajiv.
Moshe, I have a quick question. Can I get a quick question?
Yes,
and yeah,
Shankar. Yeah.
So Rajiv, if you train this on a specific LiDAR, on a specific corridor or a simulation environment, you may end up with controllers that are not robust with respect to being used on a slightly different vehicle in a slightly different environment. It may be learning some particular peculiarity of the specific LiDAR sensor it's using and so on. So is there any way to kind of control the learning so that it's actually relatively robust in terms of reuse?
Yeah, no, a great question, but I think that's more about learning. So there is this whole area of transfer learning, and so one could try to set this up as use techniques in transfer learning for that, right? Yeah, how to improve learning. Yeah.
Because I mean, what you need for that is to be able to actually, in some sense, factor the problem into the idea that the LiDAR is actually giving you a sense, a map, and that your navigation and control is actually relative to the map, and that if something else actually delivers a similar map. So it's this idea that there is actually an intermediate representation, even though your behavior is actually end-to-end.
Right. So I think so formal methods can be used in many other places than just verifications. And so I think one could try to generate additional test data, right? Yeah, like or adversarial examples, or just try to formalize what you said and then try to generate variations, right? Variations of behaviors, and make sure that the controller that you're training actually works in those variants also, right? And so there is, I think there are lots of opportunities for symbolic reasoning in this, just for learning. So even without verification, right? And so some of the things that Martin Bechev talked about were actually in that direction.
Can I say that I completely agree with that? This is Tony Hoare here.
Yeah.
Yes, Tony.
I agree with what you've just said. I would say that the main objective of research into intelligence, at least at the human level, is that we can combine sort of reflex learning, conditioned reflexes, and symbolic reasoning into an integrated survival strategy in order to learn about the real world and reason correctly about it. whereas the pure deep learning and neural network learning really are only simulating the conditioned reflex that is present in most animals. It's a view as I tend to come to. So let's set them a challenge. They're interested in real artificial intelligence. Please should they must mix verbal reasoning with the reflex reactions in a way that the human being seems to do more or less from birth. Okay, and thank you all very much. I've really enjoyed this session. And
thank you, Tony. And I'll have Shankar make a few closing comments, and then we'll send especially the people from UK and farther east, we'll send them to dinner.
Yeah,
yes,
so,
Shankar,
yeah,
please.
I just want to thank everyone for making this a really stimulating workshop. Many of you have observed, and for me as well, I have actually being here has made me realize how much I miss you guys. And this is often I get kind of I learn why I do this when I meet you in person, and being able to interact with you here is actually been a kind of revitalizing experience. So first, I'd like to thank the director and the deputy director, David Abraham and Christy Marr of the Newton Institute. I already told you about some of the Newton Institute personnel who were involved, and also in addition to Philippa and Azadeh, we had Peter Sewell, Peter Rohan, and Moshe Wadi chairing the sessions. I'd like to thank the speakers for the excellent work and genuinely addressing the theme of the workshop in a way that is extremely forward-looking. And there's just a ton of food for thought that has been generated through this workshop. And finally, I'd like to thank the audience for making this such a lively experience. So thanks everyone, and stay safe. At this point, I'm going to turn off the recording, and I will keep this running for another few minutes.
Thank you, Shankar.
Yeah.